Earth's crust is broken up into a number of large pieces called plates. Due to heat flow from Earth's core, convection within the mantle causes the plates to move along their boundaries. Motion does not occur until enough stress has accumulated for a sudden release. The plates slip along faults and earthquakes occur. Due to plate tectonics, Earth's continents have been rearranged over time. They will continue to move into the future. Plate tectonics is much more than just knowing that the crust is broken up into numerous fragments having borders where earthquakes are common. Over the next few weeks we will be looking at how plate tectonic theory has become the foundation of modern geology. If you are ever asked to name a tectonic plate, naming a continent is a safe bet. The only ocean on a plate named for it is the Pacific. People often wondered how fossils of creatures that lived in the ocean, like this ammonite, could wind up high on a mountain. Aristotle, an early Greek naturalist, as well as Leonardo da Vinci questioned how this could occur. In 1620, Sir Francis Bacon noticed that on early maps from European explorers there was a curious similarity in the coastlines of South America and Africa. He even suggested that they had at one time been connected, but separated by the biblical flood. Alfred Wegener first proposed the idea of continental drift in 1915. His theory used many sources of supporting evidence. This evidence included the apparent fit of coastlines, similar geology of the Appalachians and Scottish Highlands, identical fossils in South America and Africa, and fossils of tropical life in Arctic region. His ideas were rejected by the scientific community because he did not have a mechanism that could explain how continents could move. South America and Africa have been drifting apart for millions of years. Part of Wegener's theory was that all the continents started as one supercontinent that rifted, split apart hundreds of millions of years ago. This continent was called Pangaea. When it broke up, North and South America moved west, Antarctica slipped west and south. Africa, India, and Australia all swung east and north. The Tethys Sea closed off and became the Mediterranean Sea. India slammed into Asia, forming the Himalayas. The colors show the distribution of fossils of each species. They, and other evidence, allow us to reassemble what the continents looked like in the past. Plate tectonics became more accepted as this new evidence from the ocean floor became available. After World War II, detailed ocean floor maps were made available to researchers. These maps were discovered to show regions on the ocean floor where magnetism in the rocks was aligned with the South Pole, rather than the North. Next to these were regions with normal magnetic polarity. The ocean floor was magnetically striped. The data came from Navy records created by scanning the ocean depths with early magnetometers prior to sonar to look for large masses of moving metal, submarines, under the surface. Heat rises beneath the mid-ocean rifts. This melts rock and fuels undersea volcanism. The rising hot magma pushes the crust away on either side of the rift. Hot top expands. As the rock cools, it records the direction of the current geomagnetic field. Over time, the rock records stripes of alternating polarity because the Earth's field periodically undergoes reversals. Seafloor spreading can move the continents apart from each other, but operates very slowly. Plate speeds are on the order of inches per year. This has happened to create the Atlantic Ocean. This is happening today as the Red Sea opens wider, eventually to become a new ocean. Africa is on the lower left of this graphic. The Red Sea is between Africa and Saudi Arabia. New rock forms at the spreading center, where there is active volcanism. The oldest rock is farthest from the spreading center, rift zone. We know that the plates are moving apart here because the age of each successive region of reversed magnetism is the same as its counterpart on the other side of the central rift. Some crust is recycled at plate margins, sites where two different plates meet. We will do more with margin types and subduction zones later. Oceanic crust descends back into the mantle at subduction zones. This crust melts, destroying itself as it is recycled by our planet. This is why we have no oceanic crust older than several hundred million years. These subduction zones are also the site of deep-sea trenches, like the Marianas. What moves the plates? There are three possible mechanisms used to explain how plates move. They are convection drag, ridge push, and slab pull. The next few slides will go over these in more detail. Convection cells are like a pot of boiling pasta. The noodles rise on the sides of the pot and sink in the center, distributing the heat. Earth's internal heat is brought to the surface and released to space in the same way. Hot rock rises, cools, and then sinks. This process results in the system of mid-ocean ridges and subduction zones found all over the planet. Ridge push operates in tandem with slab pull. Rock is pushed away from the mid-ocean ridges as new material rises, heating and expanding the existing rock. As the rock moves away from the ridge, it cools. This increases its density until ultimately it runs into much less dense continental rock and sinks down into the mantle at a subduction zone. As cool, dense ocean crust sinks at subduction zones, it pulls on the rest of the plate, dragging it away from the mid-ocean ridges. Mantle convection results in convection drag, ridge push, and slab pull. All three are involved in moving plates. Above, North America is pushed away from the mid-Atlantic ridge and pulled toward the subduction zone off the coast of Asia. Asia is on the far left. NA is the continental crust in the middle. The mid-Atlantic ridge is the only ridge shown. There are three main types of plate boundaries. More information on each type will be in the following slides. Divergent boundaries are where plates move apart. New crust is formed here. Convergent plate boundaries are where plates move together. Depending on what types of plates are involved, a number of different things can happen. Transform boundaries are where two plates slide past each other. This is the type of boundary that exists between North America and the Pacific Plate. It is the San Andreas Fault. Some rifting zones begin in the interior of continents. How else could Pangaea have broken up into the modern continents? Here, one plate will sink beneath the other, forming a subduction zone and trench. The heat melts this crust, providing a source of magma. The magma rises up through fractures in the second plate, forming volcanoes. When these volcanoes rise above the waves, you have an arc of volcanic islands, a volcanic island arc. An example are the Aleutian Islands. Check out some of the effects of plate tectonics. Earthquakes also occur most frequently along plate boundaries. This is a seismogram of a magnitude 7.8 earthquake that occurred on July 22, 2020 near the Aleutian Islands in Alaska. The seismograph that recorded this is here in Michigan, at Michigan State University. It is part of our Me Quakes network, just like our station here at Chippewa Hills. Our seismograph was stored for the summer so did not record this quake. Geology could be hazardous to your health. Earthquakes cause extensive property damage. Volcanic eruptions are common around plate boundaries. Major eruptions can have global effects.